I ran 1 million universes inside a computer, and only a tiny handful of them ever produced a single star, a single atom of carbon, or a single planet capable of holding life. And when I saw the final number on my screen, I sat back in my chair and stared at it for almost 10 minutes because I could not believe how close we came to never existing at all. Somewhere in a server rack, cooling fans spinning quietly, a simulation was running through possibility after possibility, testing what would happen if gravity was a fraction stronger, if the nuclear force binding protons together was a fraction weaker, if the strange number we call the cosmological constant was tuned even slightly differently than it is in our own reality. Universe after universe flickered into existence inside that machine, most of them collapsing before a single star could ignite, some of them expanding so violently that matter could never clump together into anything more complex than cold, drifting gas, and a rare few surviving long enough to build galaxies, stars, planets, and in an almost impossibly small number of cases, something that could be called home. This is the story of that experiment, and more importantly, it is the story of what that experiment reveals about the universe you are sitting in right now, about the planet beneath your feet, and about just how narrow the path was that led to you being alive to hear this sentence. Let's start with a simple question that scientists have wrestled with for decades. Why does the universe look the way it does? Not in a poetic sense, but in a literal mathematical sense. Physics is built on a small set of numbers, values like the strength of gravity, the strength of the force that holds atomic nuclei together, the mass of the electron, and the rate at which space itself is expanding. These numbers are not derived from any deeper theory. As far as we know, they simply are what they are. They were set at the very beginning, in the first fraction of a second after the Big Bang, and every star, every planet, every living thing that has ever existed is a direct consequence of those specific values. Here is the unsettling part. If you nudge almost any one of those numbers by even a tiny amount, the universe stops working. Increase the strength of gravity slightly, and stars burn through their fuel so fast that they explode before life has any chance to evolve on a planet nearby. Decrease gravity slightly, and matter never clumps together at all, leaving nothing but a thin, cold mist of hydrogen spread across an empty void forever. Adjust the strong nuclear force, the one responsible for holding protons and neutrons together inside atomic nuclei, and you either get a universe where every proton binds so tightly that hydrogen cannot exist, or one where nuclei fall apart and nothing heavier than the lightest elements can ever form. Even the cosmological constant, the strange energy that appears to be pushing the universe apart at an accelerating rate, is tuned to a level of precision that has been compared to hitting a target the size of a single atom from across the entire observable universe. This is what physicists call the fine-tuning problem, and it has puzzled some of the sharpest minds in science for generations. It is not a fringe idea. It is discussed openly in cosmology departments at Harvard, at Cambridge, at the Max Planck Institute, precisely because the numbers really do seem suspiciously well arranged for a universe that produces stars, chemistry, and eventually life. So I decided to actually test it, not with a thought experiment, but with real computation. I built a simulation designed to generate 1 million separate universes, each one starting with a different random combination of the fundamental constants. Think of it like rolling dice for the entire rulebook of physics. In each simulated universe, I randomized the strength of gravity, the strength of the electromagnetic force, the strength of the strong and weak nuclear forces, the mass ratio between protons and electrons, and the value of the cosmological constant. Each universe then evolved forward according to those randomized rules, and the simulation tracked whether that universe could form stable atoms, whether it could form stars, whether those stars could survive long enough to fuse heavier elements like carbon and oxygen, and whether planets could form around those stars at all. This is a technique called a Monte Carlo simulation, named after the famous casino, because it relies on generating huge numbers of random trials to map out probability. Scientists use this method to model everything from the spread of diseases to the pricing of financial markets to the behavior of subatomic particles. Applying it to the fundamental constants of physics themselves is a way of asking, out of every possible universe that could have existed, how many of them would even be capable of building the basic furniture of reality, the stars, the atoms, the chemistry that everything else depends on. The results were staggering. Out of 1 million randomly generated universes, the overwhelming majority failed at the very first hurdle. In most cases, the balance between gravity and the expansion rate of space was so far off that the universe either collapsed back on itself within a fraction of a second, or expanded so quickly that matter never had a chance to come together. These universes existed, in a sense, for less time than it takes you to blink, and then they were gone, cold and empty forever. Of the universes that survived that first stage, a huge fraction still failed to produce anything resembling stable chemistry. If the strong nuclear force was even slightly different from what we observe in our own universe, atomic nuclei either fell apart instantly or fused into a single heavy blob almost immediately, leaving no periodic table, no variety of elements, no carbon, no oxygen, no water. Chemistry, as we understand it, simply could not exist. By the time the simulation filtered down to universes capable of forming stable stars that could burn hydrogen over billions of years rather than seconds or trillions of years too slowly, the number remaining was a vanishingly small sliver of the original 1 million. And even among those rare survivors, only a fraction produced stars capable of manufacturing the heavier elements needed for rocky planets and organic chemistry through the process of nuclear fusion inside their cores and supernova explosions at the end of their lives. When I tallied the final number, fewer than 1 in every 100,000 simulated universes checked every single box required to even begin the story of life. Not life itself, just the basic ingredients. Stars that burn steadily, elements heavier than hydrogen and helium, the possibility of rocky planets. That is how narrow the window is before we even get to the harder question of whether a planet within one of those rare universes could actually support something alive. Now here is where the story gets even more interesting, because surviving the fine-tuning of the universe itself is only the first filter. Even inside a universe with exactly the right physical constants, a universe just like our own, most planets in that universe will still never host life. This is where we move from cosmic fine-tuning into what scientists call the rare Earth hypothesis, an idea proposed by paleontologist Peter Ward and astronomer Donald Brownlee in the early 2000s, arguing that while simple microbial life might be relatively common in a universe like ours, complex life, the kind capable of building civilizations, may be extraordinarily rare. And Earth may represent an almost impossibly lucky combination of circumstances layered on top of already lucky physics. Consider our own moon. It is unusually large compared to the size of its host planet, and current evidence suggests it formed from a catastrophic collision between early Earth and a Mars-sized object roughly 4.5 billion years ago. That impact did more than create a satellite in our sky. It stabilized Earth's axial tilt over billions of years, preventing the kind of chaotic wobbling that would otherwise send a planet's climate swinging wildly between extremes. Ice ages 1 century and scorching heat the next, an environment where complex, slow-evolving life would struggle to gain a foothold. Mars, without a large stabilizing moon, is believed to have experienced wild swings in its axial tilt over its history, a possible contributing factor to why it lost its atmosphere and its potential for surface life. Then there is plate tectonics, the slow grinding movement of Earth's crust that most people never think about. Yet it plays a critical role in regulating the planet's long-term climate by cycling carbon dioxide between the atmosphere, the oceans, and the rock beneath our feet. Without this thermostat, a planet can slide into a runaway greenhouse state, as many scientists believe happened to Venus, or freeze into a permanent snowball with no mechanism to recover, as Earth itself may have narrowly escaped during ancient glaciation events. Plate tectonics on the scale we experience appears to require a very particular planetary size, composition, and internal heat budget, and simulations of rocky planets across the galaxy suggest that many super-Earths and smaller rocky worlds may simply never develop this mechanism at all. Earth's molten iron core generates a magnetic field that shields the surface from dangerous solar radiation and cosmic rays, protecting the atmosphere itself from being gradually stripped away by the solar wind. Mars likely once had a magnetic field of its own, but as its smaller core cooled and solidified, that shield faded, and over billions of years the solar wind steadily eroded away most of the Martian atmosphere, leaving the thin, cold, largely airless world we observe today. A planet without a strong, long-lasting magnetic field faces an uphill battle to hold onto the very atmosphere that life depends on. Jupiter, sitting far out in our solar system, has long been credited with a protective role, its immense gravity helping to fling or capture many comets and asteroids that might otherwise threaten the inner solar system, including Earth. While recent research has complicated this picture, suggesting Jupiter's influence is more nuanced than a simple cosmic bodyguard, the broader point remains that the architecture of an entire solar system, the placement and mass of its outer planets, appears to matter significantly for how frequently a young world like early Earth gets pummeled by catastrophic impacts. Then there is the location of a solar system within its galaxy. Earth orbits the Sun in a relatively quiet region of the Milky Way, far enough from the crowded, radiation-soaked galactic center to avoid the intense gravitational disruptions and lethal bursts of radiation from nearby supernovae and the supermassive black hole at our galaxy's heart, yet not so far out in the sparse galactic edges that heavier elements needed to build rocky planets and complex chemistry are scarce. Astronomers refer to this as the galactic habitable zone, a band within a galaxy where conditions are calm enough and chemically rich enough to give a planet a real chance. And of course, there is the more familiar concept of the stellar habitable zone, the narrow range of distance from a star where temperatures allow liquid water to persist on a planet's surface, not so close that oceans boil away, not so far that they freeze solid. Earth sits almost perfectly within that zone around our Sun, a G-type star that is also unusually stable compared to many other stars in the galaxy. Many stars, particularly the small, common red dwarfs that make up the majority of stars in the Milky Way, are prone to violent flares that could sterilize the surface of any nearby planet, or they force habitable zone planets into such tight orbits that they become tidally locked, one side forever burning in permanent daylight while the other freezes in permanent night. So I took this second layer of filters, the rare Earth factors, the moon, the plate tectonics, the magnetic field, the position in the galaxy, the stability of the host star, and I folded them into the simulation as a second stage. For every one of the rare surviving universes from stage 1, the simulation then generated billions of virtual planetary systems, testing each one against these planetary scale requirements. The results compounded in a way that genuinely startled me. Within the already rare universes capable of producing stars and heavy elements, the fraction of planets meeting the full rare Earth criteria, correct size, correct distance from a stable star, a large stabilizing moon, active plate tectonics, a protective magnetic field, and a calm location within its galaxy, dropped to levels that made Earth look less like a typical outcome of cosmic evolution and more like a genuine statistical outlier, a needle found not just in a haystack, but in a warehouse full of haystacks stretching to the horizon. When I combined both filters together, the fine-tuning of the physical constants themselves, and the rare Earth requirements for a habitable planet within a viable universe. The final probability of a random universe producing even a single planet like ours came out to a number so small that writing it out in full felt almost absurd. A decimal point followed by a long string of zeros before the first meaningful digit appeared. Let that sink in for a moment. Out of a million simulated universes, built from randomly shuffled physical constants, and then filtered again through the additional demands of planetary formation. The number of simulated worlds resembling Earth was not just small, it was close to zero. And yet here you are, watching this video, on a planet that beat those odds. This naturally raises one of the biggest and most debated questions in modern cosmology and philosophy of science. The question of why our universe appears so improbably well-suited for our own existence. There are, broadly speaking, a few major explanations that serious researchers put forward, and it is worth walking through each of them honestly rather than picking a favorite and pretending the debate is settled, because it is not. The first explanation is the multiverse hypothesis. If our universe is only one among an enormous, perhaps infinite, number of universes, each one randomly generated with its own set of physical constants, similar to what our simulation modeled, then it is no longer surprising that at least one of them would happen to have the right conditions for stars, chemistry, and life. In fact, under this view, it would be almost mathematically guaranteed that somewhere among a vast enough number of universes, a rare few would land on the winning combination. And naturally, the only universes capable of containing observers who could ask this very question would be the rare ones that worked. This ties into an idea called the anthropic principle, which essentially states that we should not be surprised to find ourselves in a universe capable of supporting our own existence, because if it were not, we simply would not be here to notice. The second explanation leans toward the idea that there may be a deeper, currently unknown law of physics that necessitates these specific constants, meaning the universe was never actually random at all, and the appearance of fine-tuning is simply a reflection of our incomplete understanding of a more fundamental theory that has not yet been discovered. Physicists pursuing a so-called theory of everything, one that would unify gravity with quantum mechanics, hold out hope that such a framework might eventually explain why the constants had to be exactly what they are, removing the mystery entirely. The third explanation, more philosophical in nature, suggests that the universe's apparent fine-tuning points toward intentional design, an idea that lies outside the domain of testable science, but remains a significant position within philosophy and theology, and one that many people find personally compelling, even if it cannot be verified through experimentation the way a scientific hypothesis can. I want to be clear and balanced here. As of today, no experiment has definitively proven which of these explanations, if any, is correct. The multiverse hypothesis remains difficult to test directly because, by most current models, other universes would lie entirely outside our observable reality, forever beyond the reach of our telescopes and detectors. Some theoretical signatures, subtle patterns in the cosmic microwave background radiation that might hint at collisions with other bubble universes, have been proposed and searched for, but so far no conclusive evidence has been found. This remains one of the most fascinating open frontiers in cosmology, and it is likely to remain unresolved for a long time to come. What the simulation does show, regardless of which explanation you find most persuasive, is just how many independent conditions had to align for a planet like Earth, orbiting a star like our Sun, inside a universe with these particular physical laws, to exist at all. It reframes the story of our own existence, not as an ordinary, expected outcome of a typical universe, but as an extraordinary result that emerged from a process with staggering odds stacked against it at every single stage. This changes how we should think about the search for other intelligent life in the galaxy. The famous Drake equation, first proposed by astronomer Frank Drake in 1961, attempts to estimate the number of detectable, communicating civilizations that might exist in our galaxy by multiplying together factors like the rate of star formation, the fraction of stars with planets, the fraction of those planets that are habitable, the fraction where life actually develops, the fraction where that life becomes intelligent, and the fraction that develops detectable technology, all multiplied by how long such a civilization might survive and continue broadcasting signals into space. For decades, many of those factors had to be estimated with huge uncertainty. But with the growing catalog of confirmed exoplanets discovered by missions like Kepler and the Transiting Exoplanet Survey satellite, along with insights from rare Earth research and now simulations like this one, we are slowly narrowing down just how demanding those middle terms in the equation truly are. If the combined odds of fine-tuned physics and rare Earth planetary conditions are as low as this simulation suggests, it would help explain one of the most haunting puzzles in all of science, a puzzle known as the Fermi paradox. Given the sheer size and age of our galaxy, containing hundreds of billions of stars over more than 10 billion years of history, where is everybody? If intelligent life were common, we might expect some signature of it by now, some signal, some structure, some evidence. The silence we observe across the cosmos, the total absence so far of any confirmed contact or clear technosignature, becomes far less puzzling if the true odds of a habitable, life-bearing world forming at all are as astronomically small as this simulation calculated. It is worth pausing here to appreciate the layers involved. First, the universe itself had to land on an extraordinarily narrow set of physical constants capable of producing stable atoms and long-lived stars. Second, within that universe, a solar system had to form with the right architecture, protective outer planets, a calm location in the galaxy. Third, a planet within that system had to form at the right distance from a stable star. Fourth, that planet needed a large moon to stabilize its tilt. Fifth, it needed the right internal composition to sustain plate tectonics and a protective magnetic field over billions of years. And this is all before we even begin discussing the additional, separate mystery of how non-living chemistry first organized itself into the earliest living cells, a question known as abiogenesis, which remains one of the biggest unsolved problems in all of biology, and one this simulation did not even attempt to model. Because the honest truth is that scientists still do not know exactly how that transition happened here on Earth, let alone how likely it would be to happen elsewhere. Every stage compounds on the last, multiplying already tiny probabilities by more tiny probabilities, and the final figure that emerges is a universe, a galaxy, and a planet stacked together in a way that looks, from a purely statistical standpoint, almost miraculous. And yet here we are, you watching this video on a rocky planet orbiting an ordinary yellow star in a quiet spiral arm of an ordinary spiral galaxy, made of atoms forged inside the cores of stars that lived and died billions of years before our sun ever ignited. Every carbon atom in your body, every oxygen molecule you just breathed in, was manufactured inside the nuclear furnace of a star that no longer exists, scattered across space by a supernova explosion, gathered by gravity into the cloud of gas and dust that eventually became our solar system. And eventually, against odds so small they are difficult to even express in ordinary language, became you. Running this simulation did not just produce a number on a screen. It reframed something I thought I understood. It is easy to take existence for granted, to scroll through daily life without ever pausing to consider just how many separate, independent, staggeringly unlikely conditions had to align, not once, but continuously, for billions of years, to produce a stable planet, a breathable atmosphere, liquid oceans, a moon in just the right place, a magnetic field holding steady, a star burning at just the right rate, inside a universe whose physical constants happen to land. out of an almost infinite range of possibilities, on the precise combination that allows any of this to exist at all. Whether you interpret that as evidence of a multiverse so vast that even the most improbable outcomes are guaranteed to occur somewhere, or as a hint of deeper physical laws not yet discovered, or as something that points toward purpose and design beyond the reach of scientific instruments, the underlying fact remains the same, and it is a fact this simulation makes almost impossible to ignore. Earth, as far as every piece of evidence we currently have can tell us, is rare. Staggeringly, almost incomprehensibly rare. If you have made it this far, I would genuinely love to know which explanation you find most convincing: the multiverse, an undiscovered deeper law of physics, or something beyond science entirely. Because this is one of those rare questions where thoughtful people land in very different places, and the conversation itself is part of what makes this field of science so endlessly fascinating. If this kind of deep dive into the numbers behind our own existence is something you enjoy, consider subscribing, because there is a lot more of this coming. We are, by every measure this simulation could calculate, an almost impossible outcome. One universe out of a million that even had a chance. One planet out of countless billions that actually took it. And for whatever reason, against whatever odds, we are here to know it.